In this video I intend to demonstrate a more general result. I want to show that if the velocity of a particle has the same direction of the associated wave propagation, that is, this is the momentum p, this is the wave vector k, I want to show that between the four momenta of a particle and the wave for vector a monochromatic wave, there must be a condition of direct proportionality, that is, P equals C times K, where C is a relativistic invariant and now P and K are four vectors. We assume from experience that every particle is in relation with a wave, and we make enough assumptions about the nature of this wave. We suppose only that plane wave with definitive wave number frequency is associated with a finite energy moment of a classical particle. We consider, as previously, for sake of simplicity, a plane wave of angular frequency omega traveling with wave vector k along the x-positive direction of an inertial frame S, that is, this is S, and this is a wave vector, and the x-axis. So in S we have ky equals kz equals 0, and because of a Lorentz transformation, a wave for vector, the y and z components of k will be always 0 also in any other inertial frame S prime, that is, k prime y equals k prime z equals 0. Therefore, we will look for the expression of the energy E and the component, the momentum Px, only as functions of omega and kx. And in fact, since we assume that no force acts on our system, our particle, the energy and momentum depend neither on the coordinate x nor on the time t. So our assumptions are: first, each particle is associated with a wave, and second, the finite energy and momentum of a free particle are associated with the characteristics of a plane wave amplitude frequency and wave vector, that is the energy equals a function of A, amplitude, omega and kx, and so the momentum and kx. These functions must be finite, and I put the amplitude of a wave to make things more general. And third, the momentum flows in the same direction of wave propagation as in classical physics. That is, this is the momentum, this is a wave vector, and we are going to demonstrate that the only functions allowed by special relativity are the relation of proportionality, that is the Planck equation, and the Broglie relation. And in order to show that, we need first to demonstrate that in the wave frame S0, where the momentum of the particle is 0, p0x equals 0, where wave vector is 0 as well. That is, k0x equals 0. That is, we have to demonstrate that in S0, when px equals 0, we get also kx equals 0. So our assumption was that for kx different from 0, if kx is greater than 0, it is also px greater than 0, and if kx less than 0, we get also px less than 0. This was the third assumption. And we require that such a condition holds in every inertial frame S. So let S0 be the frame which the momentum of a particle is 0. We write the Lorentz transformation between the two inertial frame S and S0 in standard Lorentz configuration for the components of the momentum and a wave vector, that is px equals gamma times beta, that is v over c times E0 over c, and for kx equals gamma times k0x plus v over c times omega 0 over c, where omega 0 is the frequency of a wave in S0, and of course beta is v over c. V is the relative speed of a frame S0 with respect to S. So we see that the sign of px only depends on the sign of v. Of course, gamma is always positive, and therefore it follows that from this equation the condition, the third assumption, is satisfied if and only if in S0 there is also k0x equals 0. That is, we have shown that from special relativity, that if p0x equals 0, we have also k0x equals 0 in S0. Of course, we could arrive to this condition if we assume the function px functions of kx continuous, but I want to use only the special relativity. Now let me go back to the main demonstration. Consider the two invariant square moduli of a four momentum p and a wave for vector k. That is e squared over c squared minus p squared s equals 0 squared c squared and omega squared over c squared minus k squared x equals omega 0 squared over c squared, where E0 equals m0 c squared and omega 0 are respectively the energy E0 and the frequency in the frames where the momentum and wave vector are 0, that is in S0. Let me start with the case m0 different from 0, that is particles with mass, and omega 0 different from 0. We have from the Lorentz transformation between S and S at 0 for the form vectors P and K. Now we mix P and K, E over C equals gamma times E0 over C plus beta times P0 x, and omega over C equals gamma times omega 0 over C plus beta k0 x, and for the momentum px equals gamma times p0x plus beta e0 over c, and kx equals gamma times k0x plus beta omega 0 over c. Now, according to our result, we assume that in a frame as 0 we have p0 x equals 0 and k0 x equals 0. The transformations, the Lorentz transformation, become the energy equals gamma times E0 and omega equals gamma omega 0, and momentum px equals gamma beta 0 over c, and kx equals gamma beta omega 0 over c. And dividing side by side these equations, we have E over omega equals 0 over omega 0, and px over kx equals 0 over omega 0. So, being the initial frame as arbitrary, from the first of these equations, we deduce the ratio E over omega has to be an invariant. Then we can introduce the invariant C, E0 over omega 0 equals C, where C is, for our initial hypothesis, finite, positive and constant with respect to the space-time coordinates t and x, and C has the physical dimensions as Planck constant, energy times time. And by confronting these equations with definition of C, we directly have that the energy equals C times omega, and the momentum px equals C times kx. And if C is the Planck constant, we can recognize in these relations, respectively, the Planck relation and the Broglie relation. And we note that from the definition of C equals m0 c squared over omega 0. Therefore, C does not explicitly depend on the amplitude of a wave A. So, we have shown that once we assume the existence of a wave, with finite energy and momentum like a classical particle, in this case particle with mass, that the momentum flows in the same direction with wave propagation, from a special relativity follows for a four momentum p and a wave for vector k a condition of a direct proportionality. Where C is an invariant under the Lorentz transformations.